The United States Liberty ship SS Richard Montgomery represents an unresolved consequence of wartime logistics. In August 1944, while anchored in shallow water off the River Medway, the Liberty ship SS Richard Montgomery dragged her anchor and grounded on a sandbank. The heavily laden cargo vessel fought to hold position as conditions worsened, but the ebbing tide and the shoal geometry left her perched fast on the bank. This stranding initiated a slow and catastrophic mechanical failure. The wartime salvage effort began immediately, racing the tides as crews started unloading the most accessible cargo. Over the following weeks, they removed roughly half the munitions, but as structural damage worsened and flooding spread, the remaining holds became unsafe and inaccessible. By late September 1944, the operation was abandoned with a substantial portion of the cargo still inside the wreck. The vessel was lost not to enemy action, but to the geometry of the grounding and the pull of gravity. When the ship struck the shoal, her flat bottom rested squarely across the highest ridge of the sand. As the tide began to ebb, the surrounding water level dropped rapidly. The ocean no longer provided hydrostatic lift to the extreme ends of the ship. The bow and the stern were left entirely unsupported, suspended over the deeper water channels on either side of the bank. A Liberty ship is constructed as a massive steel box girder designed to be evenly supported by upward water pressure along her entire length. She was never engineered to balance on a single central pivot point while carrying a massive payload. As the tide receded, the immense downward weight of the forward and aft sections took over. This unequal distribution of mass created a tremendous bending moment across the midsection of the vessel. This specific structural stress is known as hogging. The main deck plates were subjected to extreme longitudinal tension. The sheer weight of the unsupported ends stretched the upper steel far beyond its engineered yield strength. Simultaneously, the keel directly below the pivot point was subjected to crushing compression. The steel framework could not absorb the opposing forces. The heavy plating just forward of the bridge structure began to split open. The mass of the unsupported cargo holds literally ripped the hull plating apart. The ship was slowly breaking her own back. While the steel yielded to this immense pressure, stevedores and naval personnel scrambled to empty the ship. The operational priority was recovering the volatile cargo before the hull integrity failed completely. Working aboard a fracturing and unstable platform, the crews operated the cargo booms and transfer equipment to hoist the heavy ordnance out of the holds. They executed a methodical extraction under the continuous threat of total collapse, pulling out only what the weakening structure would allow. However, the shifting ocean dictated the final outcome. The structural tearing forward of the bridge opened massive fissures in the lower hull boundaries. As the tide returned, the sea poured through the splits into the forward compartments. The internal cargo spaces flooded uncontrollably. The introduction of thousands of tons of seawater added massive dead weight to the already overstressed forward section. This rapid water ingress accelerated the fracturing process. The sheer volume of water inside the vessel destroyed any remaining reserve buoyancy and dragged the broken hull deeper into the sandbank. This catastrophic structural failure and the massive flooding created a hard physical limit for the wartime salvage teams. With open breaches and uncontrollable ingress, the lower tiers of cargo could no longer be reached safely. The hull had effectively broken its back, leaving the wreck in two main sections separated by a torn midships gap. Further unloading was halted, and the site was left in place as an enduring hazard. Abandonment was a calculation. A fractured hull on a shifting tidal shoal left the remaining cargo sealed inside the wreck. The immediate wartime crisis ended, but it left behind a profound environmental problem. The confirmed dual breakage of the hull structure during the initial 1944 event established the permanent physical baseline for the site. The wartime salvage crews withdrew, leaving a severed ship and a dormant hazard locked securely in the mud. The operation ceased, leaving an open question regarding what would govern the lethal perimeter of the remaining payload in the decades to come. The dormant wreck casts a massive risk shadow over the adjacent coastline. Locked within the submerged forward compartments are approximately 1,400 tons, measured as net explosive quantity, NEQ. This isolates the weight of explosive filler itself, separate from casings, pallets, and packaging. It represents the concentrated destructive potential of the remaining cargo. This concentrated arsenal sits approximately 1.5 miles from the densely populated maritime town of Sheerness. The extreme proximity of this unexploded mass to civilian infrastructure dictates every operational decision regarding the site. Its concentration makes any accidental initiation catastrophic, forcing a lasting choice: attempt a volatile removal or keep the munitions sealed and manage the perimeter. Over the decades, authorities have favored containment over recovery. Degraded ordnance after years in seawater is unpredictable, and intrusive handling could introduce shock, friction, or impact. So the approach has centered on exclusion, monitoring, and tightly permissioned, non-intrusive survey work. Where close work is unavoidable, it is limited to external inspections, hull thickness measurements, and occasional trials with ROV techniques. The rule is simple: do not penetrate the holds and do not handle ordnance. To enforce this boundary, the government designated the wreck in 1973 under Section 2 of the Protection of Wrecks Act, creating a prohibited area around the site. It is a criminal offense to enter that prohibited area without written permission from the Secretary of State. The perimeter is marked by warning buoys, and the practical effect is a strict ban on unauthorized anchoring, fishing, diving, or salvage activity within the zone. This jurisdictional control extends beyond the surface and seabed to reduce the chance of accidental interference. In 2025, flight restrictions were introduced so that aircraft must not fly below 13,100 feet within a 1 nautical mile radius of the wreck. The combined intent is to limit low-level overflight risks while the maritime exclusion zone continues to protect the site on the water. Through this stacked system of hazard assessment and strict legislative control, the operational paradigm for the site fundamentally shifted. The state accepted the permanent reality of the underwater bomb cache and focused its entire effort on absolute containment. This rigid boundary creates a severe engineering paradox for the agencies responsible for long-term public safety. The steel hull containing the explosives is slowly decaying in a highly dynamic estuarine environment. Authorities must continuously track the structural integrity of this steel envelope to ensure the containment zone remains viable and the risk profile has not changed. This leaves the engineering teams with a singular, complex objective. They must find a way to map, measure, and monitor a degrading underwater bomb cache that they are legally and physically forbidden to touch. The estuarine environment dictates the boundaries of external observation. River sediment and fast tidal exchanges can drive visibility to near zero, making routine optical video unreliable. Aggressive currents also reduce diver efficiency and increase risk. These conditions strongly favor remote, non-contact measurement with sonar and laser scanning, providing the most dependable structure data, while diver work or video methods are reserved for tightly controlled, exceptional tasks when authorized. The wreck rests on the sandbank at an average depth of 49 feet. Because the hull sits in shallow water, the tidal variations constantly shift the currents around the steel structure, pulling heavy sediment loads directly across the site. In this opaque water column, the primary tool for non-intrusive mapping is a multibeam echo sounder mounted rigidly to the survey vessel, so the sensor can be kept stable and clear of snag hazards. Rather than towing delicate gear through a wreck site, the equipment is carried and controlled from the platform itself, allowing repeatable high-resolution passes around the structure in strong tidal conditions. The multibeam system emits thousands of concentrated acoustic pulses every second. These sound waves travel through the turbid water, strike the solid steel of the submerged wreck, and bounce back to the receiver. By measuring the exact microsecond it takes for each pulse to return, the survey software calculates the precise distance to thousands of individual points along the hull. To capture the sheer vertical sides of the vessel, the moonpool-mounted sonar head is physically rotated. Instead of merely looking straight down at the seabed, the acoustic array is angled to sweep directly across the vertical hull walls. This generates a high-density point cloud mapping the exact geometry of the submerged steel without ever touching it. However, the multibeam sonar is fundamentally limited by the ocean surface. Acoustic pulses cannot travel through the air. Because the ship rests in shallow water, parts of its superstructure, specifically the 3 towering cargo masts, protrude permanently above the waterline. The underwater acoustic sweep abruptly stops at the exact level of the tide. To capture the full structural geometry of the wreck, surveyors must deploy a second distinct technology. For the exposed sections of the ship above the water, engineers utilize vessel-based laser scanning, commonly known as LiDAR. A high-speed emitter sweeps light pulses across the protruding masts and upper works, capturing geometry that sonar cannot reach above the waterline. This creates a precise architectural model of exposed steel as it weathers in open air above the tide. The true technical achievement is the integration of two different measurement worlds into one coherent model. Survey engineers merge the multibeam point cloud with the laser scan geometry, aligning both datasets with precise positioning, GPS timing, and vessel motion reference corrections. Where the scans overlap at the waterline, the combined surface can be registered into a single, continuous three-dimensional record of the wreck. This fusion generates a continuous, non-contact three-dimensional model across both the submerged and exposed environments. The survey teams achieve their positive knowledge gain by producing a complete digital twin of the entire wreck site without ever breaking the strict physical exclusion plane. The resulting high-definition structural map pierces the zero-visibility environment, allowing engineers to examine the ship from any angle. They can strip away the turbid water digitally and inspect the bare geometry of the vessel. The success of this non-intrusive survey method transitions the operation from basic data collection to precise structural forensics, opening the exact question of what the fused acoustic data actually proves about the buckling steel below the waterline. The high-definition digital twin allows structural engineers to conduct a relentless forensic watch over 96 specific structural features across the wreck. By comparing dense point clouds from successive surveys, analysts can isolate minute changes in decaying steel over time. They are not merely looking at the ship as a single static object. They are actively hunting for signs of accelerated decay in primary bulkheads, deck plates, and the lower shell plating. The absolute focus of this intense scrutiny is the massive, coherent forward section of the vessel. This mostly intact block of the main hull acts as the primary physical containment envelope for the explosive payload. Ensuring its ongoing stability is the central objective of the entire monitoring program. Successive point clouds show the hogging-induced bend still progressing long after the hull separated. The isolated forward section remains perched unevenly on the shifting sandbank. As the estuarine currents continuously scour sediment away from the seabed beneath the wreck, the foundational support under the keel constantly changes. The steel plates are bridging new areas where the sand has been completely washed away by the tide. Gravity mercilessly exploits these unsupported spans. The immense dead weight of the internal cargo pushes down continuously against the weakening outer steel envelope. The acoustic data proves that the hull is not in a steady state of rest. It is slowly and continuously deforming under its own tremendous mass. The survey data isolates these complex deformations down to fractions of an inch. This localized analysis reveals distinct areas of severe structural distress. Engineers have identified an accelerating rate of degradation around the lower remains of the bridge structure. More importantly, the mapping highlights specific buckling patterns along the starboard lower hull. The steel in this region is physically crushing inward as the load distribution shifts. This starboard compression is a key indicator of ongoing structural fatigue. The continuous acoustic mapping confirms a much larger geometric shift driving this localized damage. The entire submerged forward section is progressively tilting eastward. This slow longitudinal roll is a direct physical response to the uneven scour trenches forming along the edge of the sandbank. By mapping this progressive eastward tilt, the survey achieves a crucial knowledge gain. It mathematically proves that the heavily laden containment envelope is actively shifting its center of gravity. However, this extraordinary structural clarity reaches a hard, impenetrable boundary at the steel plating. The external acoustic sweep maps the outer geometry of the wreck with absolute precision, but sound waves reflecting off the hull cannot see through solid metal. This creates a permanent proof ceiling regarding the internal conditions. The intact forward holds remain a completely sealed environment. The multibeam sonar provides zero data on the current orientation of the individual wooden cargo crates. Engineers cannot verify if the stacked tiers of munitions have collapsed internally due to the ongoing eastward tilt. The structural experts can measure the bending of the external hull down to the inch, but they remain entirely blind to the friction happening inside. The actual chemical stability of the explosive filler and the physical state of the bomb fuses locked inside those darkened compartments cannot be directly observed. The internal bomb cache remains an absolute black box with its true volatility inferred but never proven. With that limit accepted, the analysis turns back to what exterior geometry can still show. The data confirms the forward section is intact enough to safely contain the ordnance, yet structurally compromised enough to actively deform under the shifting tidal environment. The acoustic imagery also clearly defines the harsh boundary where this coherent forward section abruptly ends. The original fracturing event sheared the vessel completely, leaving a wide, chaotic trench on the seabed before the remnants of the stern. As the forward mass tilts further eastward, the structural integrity of the site depends on understanding exactly what lies in the fractured void separating the two distinct halves of the wreck. The wide trench separating the two immense halves of the vessel functions as a massive underwater geometry trap. When the vessel originally broke apart, the steel did not shear in a clean surgical line. The midsection tore violently, ripping through decks, framing, and bulkheads. Today, the powerful tidal currents sweeping across the sandbank accelerate as they squeeze through this jagged corridor between the bow and the stern. This focused hydrodynamic energy continuously carves out a deep scour pit in the seabed directly between the surviving hull sections. The physical void created by the original fracture has evolved into an active catch basin for everything that detaches from the wreck. High-definition acoustic mapping isolates the specific boundaries of this spillage and scour perimeter. Survey engineers analyzing the empty space between the hull blocks identified dense concentrations of scattered material. The data reveals large collapsed sections of the original bridge structure lying semi-buried in the sediment. As the decades pass, severe atmospheric corrosion eats away at the exposed upper works. When these heavy steel components finally yield to the elements, they do not float away. Gravity drags them straight down into the scour gap. By mapping the precise layout of this localized debris field, the survey achieves a distinct knowledge gain. The acoustic shadows suggest that heavy structural shedding is largely concentrated within the central trench between the two main hull sections. Detached plates and beams tend to settle into the scour feature rather than spreading widely across the estuary, though individual contacts can be buried, uncovered, or shift as sediments move. The footprint is therefore treated as concentrated in the gap and continuously monitored, not assumed to be immobile. Interpreting the scatter is a classification problem. Sonar returns can confirm metal targets in the pit, but they cannot identify whether a given contact is torn hull plating or spilled cargo. Because the midsection fractured so violently, planners must assume at least some items from the adjacent holds may have entered the gap during the initial structural failure. This uncertainty creates a hard local proof limit. Because the seabed lies inside a prohibited area and the remaining cargo is treated as a live hazard, intrusive excavation and routine recovery are not pursued. Any entry or work within the zone requires written permission, and operational practice is to avoid disturbing unidentified targets in the trench. The anomalies are logged, resurveyed, and watched for movement rather than physically turned or collected. With the trench recorded and left undisturbed, the surveys shift to what the debris pattern implies about the wreck above. The analysis of these detached components confirms a grim reality about the ongoing deterioration of the wreck. The ship is actively shedding its upper mass. The collapsed bridge fragments resting in the trench prove that gravity and corrosion will eventually tear down anything left standing above the waterline. While debris falling into the empty scour pit is easily absorbed by the seabed, the shedding process creates a drastically different hazard profile elsewhere on the ship. The data from the debris field forces engineers to look upward, opening the immediate operational question of what must happen when the tallest surviving structures threaten to collapse directly onto the sealed cargo holds below. For decades, the long-term management condition of the wreck site was defined by strict restraint and minimal disturbance. However, monitoring has highlighted a specific external trigger risk. The three masts that still protrude above the waterline may eventually fail and fall onto the wreck. In 2021, the government announced its intention to remove the masts to reduce that impact hazard. and preparatory survey work was planned for autumn 2022. Subsequent assessments identified significant engineering challenges, so the project has been reviewed, while alternative approaches are developed. The objective remains narrow and protective. Reduce the risk of a mast collapse striking the wreck without disturbing the munitions or attempting cargo recovery. This intervention is not a move toward recovery. It is a conditionally permitted action to remove a secondary external hazard, the masts, so their failure cannot deliver a kinetic shock onto the wreck. The mandate on the explosive payload remains unchanged. No penetration of the sealed decks, no ordnance handling, and no physical contact with the submerged main hull. The state is authorizing only the removal of the upper works to protect the containment envelope below. By planning this surgical removal, the authorities successfully mitigate the most immediate and predictable trigger mechanism. Yet, removing the warning masts does not neutralize the underlying payload hidden in the mud. The overarching legacy of the vessel is a permanent, heavily guarded watch list. Those restrictions remain in force. Passive containment will continue to govern the coastline. Tidal currents will keep working the sandbank around a payload that remains in place, while repeated non-intrusive surveys maintain a disciplined watch for structural change. It is an enduring standoff, slow decay measured from the outside, and a sealed interior that cannot be safely accessed.